Hello and welcome to Lecture 1 of the Electric Current unit in Phys 1204. We've met a bunch of new physical quantities over the last few units, electric potential, electric field, and so on. Now it's time for another one, electric current, which describes the motion of charges in a system. Well, I'm going to start with the rather painfully obvious statement that capacitors are not like light bulbs, but I mean something specific by that. When you connect a battery up to a capacitor, then it does work by moving charge from one plate to the other, and as it does so, it's converting chemical energy in the battery into electric potential energy, which is stored in the capacitor. But that process doesn't go on for very long. The whole system ends up in electrostatic equilibrium rather quickly, at which point no charge is being moved around anymore, and so the battery stops converting chemical energy into electric potential energy. On the other hand, when you connect a battery to a light bulb, the battery keeps doing work. Because to make the light bulb work, it is pushing electrons out of the negative terminal of the battery, they're pushed through the light bulb, and they arrive back at the positive terminal of the battery. And this process just goes on, and so the battery is continually transporting electrons from its positive terminal to its negative terminal, doing work on them in the process. And so it's converting chemical energy here into light, which isn't energy but does carry energy, and in most light bulbs into thermal energy as well. But unlike with the capacitor, that process will eventually run down because the battery is consuming its chemical energy, since it's continuously converting it into other forms. Notice that what we're now talking about is a cyclic process. Think of something like the water cycle, where if for some reason the evaporation stopped happening, there would now no longer be a supply of water to condense into clouds, to be transported elsewhere, and to precipitate out. Removal of any part of the process stops the whole process. Circuits are just like that. The electrons have to be able to flow all the way around the circuit. They have to leave the negative terminal of the battery and eventually arrive back at the positive terminal of the battery. Otherwise, positive charge builds up at the positive terminal of the battery, and the electric fields that result from that will eventually stop the flow of electrons. That's exactly what happens when a battery is connected to a capacitor. The buildup of charge on the plates sets up electric fields, which eventually stop the flow of electrons in the system. And this is happening because there is a break in the circuit, and so electrons that leave the negative terminal of the battery are unable to make it around to the positive terminal of the battery. If we take a circuit consisting of a battery and a light bulb and we snip one of the wires, then we've inserted a break into the circuit. And because the battery is pulling electrons away from one end and pushing them on to the other, charge would build up at that break, just like it would for a capacitor. In fact, it really is a capacitor, it's just a very, very low capacitance capacitor. And like a capacitor, it will very quickly stop the flow of electrons in the circuit. You can see this in the design of electrical components. If you look closely at a light bulb, you'll notice that it has two terminals. The reason it has to have two terminals is that there has to be one place for electrons to enter the light bulb and another place for them to exit, because they must pass through. By the way, a light bulb doesn't care which terminal the electrons enter or exit. They can go either way through the light bulb and it will work, although there are some other electrical components where it does matter which way the electrons flow through. In any case, this means that if you take a battery and a light bulb, you cannot light the light bulb by simply connecting one terminal of the light bulb to one terminal of the battery, no matter which terminal you use. You have to connect one terminal of the battery to one terminal of the light bulb and the other terminal of the light bulb to the remaining terminal of the battery. That allows an electron current to flow, by which we mean that electrons come out of the negative terminal of the battery and flow around in what we refer to as the electron current until they arrive at the positive terminal. The electron current is usually measured in a number of electrons per second, and you may guess that measured that way it tends to be a rather large number, since a wire will have a lot of electrons in it. One other thing to realize about circuits is that charge does not collect anywhere in a circuit other than on the plates of a capacitor, except remember that the charge on one plate of a capacitor is always the negative of the charge on the other plate, and so the total charge on the capacitor is always zero. You can see this experimentally very easily, because we easily observe effects when charge collects anywhere. If you're near it or particularly touching where the charge is collecting, your hair tends to stand on end, and you usually notice that. And if a lot of charge collects somewhere, then breakdown will occur and sparks will jump. Normally, you don't have either of those happening in a typical circuit, and that tells you that no charge collects anywhere in a typical circuit. A useful piece of terminology is power sources and loads. A circuit generally always consists of a power source and a load. The power source could be any number of things. It could be a battery converting chemical energy into electric potential energy, or perhaps a generator doing the same conversion but by a different means. It could be a photovoltaic panel converting energy carried by light into electric potential energy. It could, in a very large circuit, be a hydroelectric dam converting gravitational potential energy into electric potential energy, or any number of other possibilities. The common theme, however, I hope you notice, is that all of them are turning some form of energy into electric potential energy. Meanwhile, the load can be any number of things. It could be a light bulb converting electric potential energy into energy carried by light. It could be a heating element converting electric potential energy into thermal energy, or a motor converting electric potential energy into mechanical work being done on some object. But again, the common theme is that they are all converting electric potential energy into some other form of energy. Well, it's been too long since you and your friend Sam have had a disagreement over something, so here's one. You and Sam are observing who walks down a hallway, and you're going to compare notes later. And at some point, you notice that Psy, Elvis, and Macklemore walk past you. Well, comparing notes later with Sam says that only Elvis and Macklemore walked past. Well, wait a second, something's fishy. What happened to Psy? Was there a secret trap door that he jumped down? Is this all a hallucination? Did Elvis and Macklemore eat Psy? I don't think we believe that Psy just spontaneously disappeared. I think we will agree that there is a law of conservation of people. And people don't just disappear as they're walking down hallways. Likewise, they don't just appear as they're walking down hallways. So if Sam reported that Psy, Elvis, and Macklemore and Olaf the Snowman walked past, you would be equally surprised. So, more generally, if you counted what we might call people current of 90 people per hour passing you in the hallway, as long as there are no doorways or branches in the hall that other people can go down or come in from, Sam ought to certainly report the same 90 people per hour as the observed people current. Any other number either means people are being created or destroyed, and we don't really expect that to happen in a typical hallway. Likewise, charge is conserved, just like people walking down hallways, and in particular things like electrons are conserved. And so the rate at which charge passes by points on any unbranched path must always be the same. And when I say on an unbranched path, I mean as long as there are no junctions or other ways that current splits or comes together. Well, let's check your understanding. So here's the very simple circuit of a single battery and a light bulb, and there are 2 points, A and B, so that as the electrons are going around this circuit, they pass through A, then they pass through the light bulb, then they pass through B. Well, which is greater, the electron current through A or the electron current through B?